Hello and Assalamu alaikum students. How are you guys doing? I hope everyone is fine. This is our lecture number 7 of signal processing class, and in this lecture we will continue studying discrete Fourier transform or DFT. We will cover following topics including analysis equation to transform signal from time domain to frequency domain, calculating DFT by three different methods, which are by simultaneous equations, by correlation method, and by fast Fourier transform. And at the end, synthesis equation to transform signal from frequency domain back to time domain. Here, analysis means transforming a signal from time domain to frequency domain. It is done so by calculating discrete Fourier transform, and there are three methods for calculating discrete Fourier transform. One is by simultaneous equations. This method is very useful for developing the understanding of DFT or discrete Fourier transform, but it is too inefficient for practical use because it involves too many equations. And the second one is by correlation method, and correlation correlation is actually used to find out the similarity between two signals. This method can also be used for calculating DFT. And third, and the preferable one and the most efficient one, is FFT, which stands for fast Fourier transform. It is an ingenious algorithm, very efficient, which decomposes DFT with n points into n DFTs with a single point. So this one is a very efficient one. It requires only a few lines of course, but behind it there is complicated mathematics involved, but we do not need to go into details. Only a few lines of course in Python or MATLAB or any other coding software that you are using, we can accomplish fast Fourier transform. Okay, by simultaneous equations we can calculate DFT, and the simultaneous equations, you are familiar with this term, that in algebra we use the simultaneous equations to find out values of unknown variables, right? So you also know that the number of simultaneous equations required to find out certain number of unknown variables must be equal to the number of unknown variables. For example, if there are for example 4 variables, you need 4 simultaneous equations to solve for those 4 variables, to finding out the values for those 4 variables. So in this case, a discrete signal, each point in the discrete signal is considered as one variable. So it means that we need uh, uh, if we need one equation for each point in the signal. So let us consider there are n points. There we will need n equations for to calculate the DFT for that signal. For example, if a signal is like 64 points long, there are 64 samples of a signal, we need 64 equations to find out its discrete Fourier transform, okay, or calculating its discrete Fourier transform. So and 64 is a very small one. Like if we have 1000 points in a signal, then we will need 1000 simultaneous equations to solve that. So that is why it is a very inefficient one, but by doing that we go into extensive work, and it helps our understanding of DFT stepwise. So unfortunately this method requires a tremendous number of calculations and is virtually never used in DSP or digital signal processing. So if we want to start understanding DFT, we can use it for smaller signals with our programs in MATLAB or on paper, but in actual practice we normally do not use it. And by correlation method, this is the analysis equation. So this is the equation that is used to calculate DFT by correlation method. And this equation is called as synthesis equation, and we have seen this in the previous lecture also. And it consists of two parts. This part, the one with the sine and the with the cos, and the other one with sine. So one part is called as real part, and the other one is imaginary. The one with the cos is real part, and the one with the sine is imaginary part, and they are represented with Rex and Imx respectively. So the one with sine is called as imaginary part of x, and the one with cos is the real part of xk. So you remember from the notation that capital represents, means the capital letter represents the signal in frequency domain, and the small letter, it represents the signal in time domain. So you notice that the one on the left hand side of the equation is the one that we are getting, means the output. This is the frequency domain. In the frequency, normally we call it spectrum instead of signal. So this is the frequency spectrum, or the signal in frequency domain. And xi, this is, it is written with small letter. This one is the signal in time domain, and there is another difference. There is k and there is I, in order to differentiate the samples of time domain signal and frequency domain. And the sum, it runs from I0 to n minus 1. I0 is, means I is actually the sample number of time domain signal, okay, and k is actually the sample number of the signal or spectrum in frequency domain. So it runs from 0 to n minus 1. N is the total number of samples, means if there are 100 samples, it will run from 0 to 99. Okay, so total number will be 100 because it includes 0. So 0 to n minus 1 means all the samples. For example, if a sample has 60, if a signal has 65 samples, so it will run from 0 until 64. And similar is the case on the other side. Also notice that the sign or the imaginary part comes with negative sign. Okay, so the summation on both sides for both parts is running for I, not for k. Okay, so remember, this is for I in both cases, from 0 until n minus 1. So you have to take a note of it, because there is another similar equation that will come at the end. Okay, that looks exactly the similar, but that does not run from I, that runs from k. Okay, that is a synthesis equation that will come in the later part of this lecture. Okay, now let us take a closer look at how it works. Let us consider these two example signals. One is called x1, written here in the legend, and the other one is x2. Both look similar in a way that both are sinusoids. This one is a sine wave, as you can guess. It is starting from 0. This is a sine wave which is completing its 1, 2 and 3 cycles within 64 points, 0 until 63. There is no 64th point here. Okay, so total number of samples are 64. So this is a sine wave which is completing its 3 cycles in 64 samples. And on the other side, x2 signal is another signal different from x1. It is a combination of sines and cosine waves, means we have added a couple of sine and cosine waves, and result is this one. But these are made in such a, means the signals which are added here are purposely those which does not include a sine wave of this form, means a sine wave that is completing 3 cycles or has a frequency of 3. So this signal is not included here. So maybe we have added cos of frequency 5 Hertz and sine of frequency 4 Hertz plus another cos of uh, 2 Hertz, but it does not include this signal. Okay, so we have purposely not included to keep a difference. Now by correlation method, as you saw before, that it is used to find out the known waveform. So the known waveform, we need to have one waveform, okay, that we will use by correlation method to find if that exists in that sample or not. Okay, so that known this one, this is a sine wave. You notice here on the top it is S3 basis function. You have seen previously S3 basis function means that function of sine, okay, with 3 frequency, or in the given number of samples it is completing its 3 cycles. There will be many, there are n over 2 plus 1 uh, basis functions for this one, for this, sorry. Okay, so for this signal x1 there can be n over 2 plus 1 similar basis functions for S, and for C also. C means cos. So this is from those we have selected one only to see the correlation between this signal, which is a known one, and x1 signal. So we try to find out the similarity or correlation between this signal with x1 and x2. Okay, since we have seen that that x1 is actually a sine wave of 3 cycles within 64 samples, and this one is also a sine wave with a subscript of 3, means that it has 3 cycles. Okay, so just to help you out, there will be an S2. S2 means that sine wave of 2 cycles here within this range from 0 to 64, and there will be an S1 also that has only 1 cycle, and there will be an S4 that has 4 cycles, and there will be an S5 that will have 5 cycles here. So out of all those we have selected only one, which is S3, to see the correlation. Okay, okay, now we will see that if that exists in there or not. To do so, we multiply these two signals, S3 and X1 and S3 and X2. We multiply. After multiplication, here you can see in the legend X1 times S3. So after multiplication, you multiply each point of X1 with S3, and you will see that even the negative part of the signal goes towards positive on the positive side, because on the negative side it is all the values are in negative. When the negative multiplies with negative, it becomes positive. So this trough will go up again. It looks like a full wave rectifier. Okay, so full wave rectifier can be used to do this, of course. So when this thing happens, it means that all the resulting, the sum of all these is equal to a positive number, right? So if there is a positive value, it means that there is some correlation between the signals which are multiplied together. Okay, so we can calculate actually using our equation that the sum of all these points should be equal to 32. Okay, so if it is 32, means that these two signals x1 here, x1 and s3, they are correlated with each other. And on the other hand, we multiply s3 with x2 also, and we get this type of spectrum. You can do it yourself because there are only few points. Maybe you can try on your notebooks for one cycle only, like from 0 until sample number 16, and maybe sample number 20. You can try until that and then see whether you get these values or not. It is very simple. Okay, but when you look at this one, which is the multiplication of x2 and s3, you will get this one. When you add up all of them, you will get 0. some part is negative, some part is positive, and when you add them together you will get 0, means that the amplitude is 0. The reason, because in x2, this example signal, there is no component. When we actually made this signal by adding up multiple sines and cosine waves, there was no component of S3, means S3 was not there. A signal that has 3 cycles in 64 points, or you can say that a signal with 3 frequency was not used in order to make up this signal. Therefore, there is no correlation between S3 or sine wave of frequency 3 with x2 example signal. So some of these points will be equal to 0 and some of these points will be a positive number and 32. Okay, so this is how we find out. So by doing that, actually we have to do it for every different component. I means every other component of this signal, like S1, S2, S3, S4, to find out which ones actually contribute to that signal, because you know from Fourier series that we can decompose one signal, means we can decompose any signal into a combination of sines and cosine waves, right? So we keep on doing for different combination of sines and cosines to find out which of the signal, means which of the frequency of sine or cosine wave actually exists in that signal. Okay, this is the means a combined image of that. So this was x1, this is x2, this was the one that we were looking for to find in the example signals. So when we multiply each point with every other, means first point with first point, we get this, second point with second point, we get this. So we are doing that to find out the correlation between these two signals. Okay, and similar is the case here. This one will give us zero sum, means we add all of them together to get 0. We add all of them, we will get a positive number and hopefully 32. So this one shows that this component exists here. So we can keep on doing. This was for one point only, that was IMX3. IMX is the imaginary part of the analysis equation of 3 frequency, third component, this one S3. So this is just for an example. There will be from 0 to n over 2 plus 1. So from all of those we have chosen only one just for giving a demonstration. Okay, so the amplitude of this one is calculated by a different formula that will come later on. Okay, so this is actually the imaginary, this is one point of imaginary x, imaginary part of the x, or imaginary part of the analysis equation, and third point of that, third sample of that. Okay, so third sample means that S of 3 cycles in the given range. So there will be a 4 where there will be 4 cycles, then there will be a 5 here with 5 cycles, and so on until n over 2 plus 1. Okay, so n over 2 plus 1, if there is 64 samples, so n over 2 of 64 is 32. Okay, and 32 plus 1, so 33. There will be 33 components of S or imaginary, and 32 for real X. But out of all those we have chosen only one for demonstration purposes. Okay, now we come to the DFT calculation by fast Fourier transform. So this approach produces same results as others, like by correlation and by simultaneous equations, but it is faster and efficient as it requires only a few lines of codes to do the task. So, and it involves three steps. First step is decomposing n-point time domain signal into n time domain signals, and each consists of one point only. Means that if there is an n-point signal in time domain, n-point means, let us consider 64 points in time domain, then we need to decompose that time domain signal into 64 signals. Okay, if n was 64, then we have to decompose that time domain signal into n time domain signals, or 64 signals, and each signal will consist of one point only. So first step is decomposing, and second one is calculating the frequency spectra of each of those single point time domain signals. Okay, so when we decompose an n point time domain signal into n time domain signals, so each of those consisting of one single point, so each of that will actually act as a time domain signal. We have to convert that each n point means n signals into n frequency spectra, means each of that signal will be converted into frequency domain, will be transformed into frequency domain, means there will be 64 frequency spectra after step number 2. And in step number 3 we have to combine all of those to make one signal. Okay, so we have to combine these n frequency spectra to form a single frequency spectrum, which is the frequency domain representation of the original signal in the time domain, right? So that is our purpose, to transform from time domain into frequency domain. So these are the three steps involved in calculating discrete Fourier transform with the help of fast Fourier transform. Okay, now let us take a look how it is done. First step is the decomposition. Okay, so let us consider we have a signal that is composed of 16 points, this one. So these are the these are the point numbers or sample numbers. This does not actually represent the amplitude, this is just the number of samples. So first sample is 0 sample, second sample is 1 sample, the number of second sample is 1, and the number of third sample is 2, and so on until 15. So total there are 16 points in this signal. Okay, time domain signal. Now the first step is to decompose. How to decompose? It is very interesting here. We decompose first, means we decompose it into two parts. At every step we decompose the existing signal into two parts. So one part contains even number of samples, means even numbered samples, and the other part contains odd numbered samples, means first part contains 0, 2, 4, 6, 8, 10, 12 and 14. From here means all the even numbered samples, and then second part all the odd numbered samples, 1, 3, 5, 7, 9, 11, 13 and 15 in the other part. Then on this next stage, each of these is further divided or decomposed into two more spectra in a similar fashion, even in one and odd in the other one. So now here these samples are 1, 2, these are 0, 1, 2, 3, 4, 5, 6 and 7. 0, 1, 2, 3, 4, 5, 6 and 7. Now the number is changed. Now these no more represent the sample number. Okay, so the sample number must be 0, 1, 2, 3, 4, 5, 6 and 7. Okay, here now these are, we can, this number of samples is, the sample numbers are changed. Now this is 1, 2, 3, 4, 5, 6 and 7. Now these are the even ones which will go here. You can see this. and the odd ones 1, 3, 5 and 7 go to this one, right? So this is how the sample numbers are. We have even sample numbers, one in one part of the decomposed signal and odd in the other one. Similar is for this case. So this is now 0, 1, 2, 3, 4, 5, 6 and 7. So the even ones, these are the even ones now, they are going here, and odd ones are going in the second part. And again, now in this case, in the next step, this is 0, 1, 2 and 3. So even are this and this, we send them here, and here these are even, we send them here, and these ones, or in other words, you can just say that we add alternative points into we split with alternative points. So first here, second here, third here, fourth here, like this. So it is up to you how you want to understand it, but we can say that even numbered samples and odd numbered samples are separated into two decomposed parts of the signal. So we keep on doing until we get signals with 1 point each, only 1 point. We are left with only 1 point. Now you see that the first sample after rearrangement is the same, and the last sample also remains the same, but all others are changed. So this one is now here. So this one now goes here, okay, and 2, this one goes here, right? So that's how the arrangement of the samples is changed, and this arrangement is actually, it has an order that I will explain to you after a while in the next slide. This type of decomposition is called as interlaced decomposition, okay, and these number of stages, the number of stages which are required to get 1 point signal from a given from a given signal depends on the number of samples here, and it can be found out by this formula, log base 2n. This log base 2n This log base 2n, here capital N is the number of samples. So using this we can calculate how many number of stages will be involved in getting 1 point spectrum or from the given signal. So just for example, for this case we have n is equal to 64, n is equal to 16, right? It is equal to 16. So using this formula, log base 2, how we can calculate? So we the number of stages we can say, let us say x is the number of stages, right? So x is equal to log base 2 of n is 16, right? So here we can write it like this: x raised to the power 2 is equal to 16. We can write it like this. Well, then what raised to the power x will be 16. So we take square root on both sides. It is equal to 4, right? So 4 stages must be involved in decomposition of a signal with n points, 16 points to 1 point signals. You can count 1, 2, 3 and 4. So 4 stages were involved in decomposing a signal consisting of 16 points into 1 point signals, right? Okay, let's go to the next one and how this arrangement is working. Now you just take notice that 0 and 0, then there is 8, 4, 12. So these are arranged now. Actually, there is a rearrangement of the samples. It is there is a order in this rearrangement, like given here. So here you can see, if you wait. Okay. This order, you can see this was the normal order. Zero number of the samples, sample numbers, 0 sample 1 2 3 until sample number 15 in the previous slide, right? So this was the new order after decomposition. So 0 4 8 4 12 2 10 16 and so on until 15. So you remember from the previous slide that 0 was staying at its own position, the last one was at its own position also, and in between there were a shuffle or rearrangement. And that rearrangement, if we convert these numbers into binary, tells us a different, tells us an arrangement. So 1 is represented in binary like this, okay, 4-bit binary 001, and 2 is represented 0010, and so on until 15 we have like this. So and then we convert these into binary also like this, and then when we see these, we see reversal in the bits, like here it was 0001, and after rearrangement it is 1000, right? So this is the reversal of bits. In the second one, 0010, now it is 0100, and let's say check the 7, 0111, and the corresponding number is the 7th in the rearranged one is 1110. So this is the bit reversal. So we can simply use this bit reversal instead of going through all that decomposition steps. We can use this bit reversal arrangement or bit reversal observation in decomposing the signal directly from the normal arrangement, like in these samples, to one sample signal by arranging the sample numbers in this order by bit reversal. But going beyond 15 will be different story. So that's why if we have until 15 or less than this, we can use this binary, but after that it becomes difficult. Okay, so FFT time domain decomposition can be implemented by sorting the samples according to bit reversed order. Okay, so instead of going through all those steps, we can simply use this observation of bit reversal to decompose our time domain signal into n frequency domain signals. Here each of these is one signal. Okay, this is one full signal, and by arranging these we get one signal for each of these points. So 0 is one signal, 8 is one signal, 4 is one signal, 12 is one signal, but here one signal is composed of all these points, right? So that was the first step of decomposition, and then the second step is converting the the n time domain signals into n frequency spectra. Means that once we get all those n signals, we have to convert each of them into, or we have to transform each of them into frequency domain, right? So in the frequency domain, 1 point signal is actually equal to itself. We do not need to convert it. Okay, so that one the conversion is not required, but as a process, then we can consider that the 1 point signals are in frequency domain now. Okay, they are no more in time domain. We will not represent them on time domain or with small letter. We will represent it with capital letter, and we will say that it is in frequency domain. And then the last step, the final one, which is the synthesis of FFT, in which we combine all of those frequency domain signals into one frequency domain spectrum. And for doing so, in order to do that, we have to go step by step in reverse order to the interlacing that happens before in decomposing the time domain signal. We have to go in reverse to make frequency domain spectrum. Okay, now how it is done is by looking at this, how we go to back, like if you remember that by decomposing one signal was in splitting it into two, like a 16 was divided into two 8-point signals, then each 8-point signal was divided into two 4-point signals, and each 4-point signal was then divided into two 2-point signals, and then each 2-point signal was divided into two 1-point signals, right? So by we were dividing into half. Now in frequency, now in order to stitch them together in frequency domain, we have to double up, like we will combine two 2 points into one 4-point signal, and then two 4-point signals into one 8-point signal, means we are going backwards. Like here in time domain, if it happens in time domain, we represent it like this. Let us consider two spectra in time domain and two corresponding spectra in frequency domain. Frequency domain representation is with capital letters and time domain is in small letters. So in order to convert two 4-point time domain into one 8-point time domain, we do it like this, that we make one 8-point signal from this and one 8-point signal from this. These are two time domain signals that we will combine into one 8-point signal. Okay, so A, B, C, D is one, E, F, G, H is the second one. So we space them apart with alternative zeros in between. Since these are 4, we have to make an 8-point signal, right? So after every sample we will put a blank space, and blank space will be filled with 0. We will do the similar thing with the second spectrum, sorry, with the second signal, but in this case we will shift it first. By shifting, we are going to add 0. Okay, shifting is done, you remember that we can do the shift by convolving with a shifted version of shifting version of the impulse signal. So we multiply a signal with a shifted impulse, we get 1-point shift in that, or as many mentioned in the as many points as the impulse signal is shifted. So we shift the impulse signal with by 1 point, okay, and then do a convolution with this signal and it will be shifted also. This is the procedure of shifting. So we shift it and then we do the same thing, alternative zeros in between samples. Now it is done in order to make the length equal and also helping adding them together. So the non-zero one, or the first sample, when we add them together, we merge them together, this will be added with 0, okay, and it will not change its identity. A will come here and then E will go there, and B will come at this place, F will go there, C will come here, and that's how we will add them together. But in frequency domain it is different. In frequency domain we do the duplication. Okay, instead of adding zeros we do the duplication. So first we add ABCD like this, ABCD, first 4 points, and then second 4 points again ABCD. This is the duplication. Okay, and then for the second one, EFGH, this is the one in time domain which was shifted, okay, by 1 point. So this one will be multiplied with the sinusoid, and then duplicated. Okay, so when this thing happens, when this thing is done, ABCD is duplicated and EFGH, the second signal, is multiplied with the sinusoid and then duplicated. After that we add both of these signals together, okay, and we get one frequency domain spectrum. This process is graphically represented. This process is graphically represented with this image. So this is a graphical illustration of the synthesis of fast Fourier transform. So look at this like this. So the even 4-point spectrum, the previous one like this one, this is duplicated, okay, without multiplication with sine or cosine. So this is, we call this even 4-point frequency spectrum. It is going straight. This is the final 8-point spectrum, frequency spectrum, okay. So by adding these two, right, so even ones are going straight, okay, without multiplication with the sinusoid, and these we call them odd ones. So odd 4-point frequency spectrum are first multiplied with sine or cosine. These are the sinusoid waveforms. So these are multiplied with sinusoid waveforms of an appropriate frequency, okay, and then added, okay. First they go straight and then they are combined with the other ones also, because we have to add them together, right, like this. So by doing so, first the 4 points are going without any multiplication with the sinusoid waveform, and then the next 4 points are multiplied with the sinusoid waveforms and duplicated and then added with the even ones, okay. So even ones without multiplication with sinusoid waveform and but with duplication, and the odd points with multiplication after multiplication with sinusoid and then duplication, okay, then they are added together, okay, to form one 8-point frequency spectrum, okay. It's the basic component and the simplest element of FFT. It is called as FFT butterfly because of its uh, wing-like shape. So that for this reason it is called as FFT butterfly, and it is the simplest and basic form of the FFT, this part. So this one is repeated over and over in this uh, graphical representation, okay. So 2 points, one is the even, one is the odd one. The even one does not multiply with the sinusoid, odd one multiplies with the sinusoid and then duplicated. So the even one without multiplication the sinusoid, it is duplicated and then both are added together and give us 2 points, okay. So this is how it is graphically represented. The overall process is represented with this flow chart. So the signal starts with the time domain, okay, the bit reversal and data sorting uh, is done here, okay. So the bit reversal, data sorting, as we have seen in the previous slide, this is the decomposition, actually time domain decomposition by bit reversal, data sorting, and then the loop comes here, in which there is the calculation of the FFT composition. Means we have to combine the frequency domain spectrum, okay, that is called as frequency domain synthesis. So this part is the decomposition part, and the second part is the synthesis part, okay. So there is, you cannot see here the conversion of time domain into frequency domain, because the time domain, when they are in single point form, they are already equal to their frequency counterpart, okay. they are equal to the frequency domain spectrum. Okay, so after that we need to combine them. Okay, as we saw in the previous slide. So the frequency domain spectrum is synthesized using these loops. Okay, and then at the end we get frequency domain spectrum. Okay, so these are the three steps involved in fast Fourier transformation. Now, in order to get our time domain signal back, we need to perform inverse DFT to bring this to transform the signal into frequency domain. We used DFT or discrete Fourier transform. Now in order to bring our signal back into time domain, we need to perform inverse DFT, and this is done by using this synthesis equation. Now you see that this one is the output is a time domain signal. Okay, and here it is the frequency domain representation. Now you have to notice that this equation is very similar to the analysis equation that we saw in the earlier part of this lecture. The only difference is that here it was written xi and the sum was starting from I to I equals to 0 to n minus 1. So these are the two differences in synthesis equation and the analysis equation. Okay, so in this one here, this part, this is the amplitude of cosine wave and this is the amplitude of sine wave. These are the basis functions. Cos 2 pi ki over n is the basis function and sine 2 pi ki over n is another basis function. These are two basis functions. So this one is represented with ci and this one with si. Okay, you have seen this in the previous lecture. So these are the basis functions and these are the amplitudes. So these two are the amplitudes and the others are the basis functions. We can find out amplitude as we have seen in one of the slides previously, but how we can calculate is very simple. So in order to calculate the amplitude of real part, means for the amplitude of cosine waves, here we divide Rex. This Rex comes from the synthesis equation. Remember the real part of the synthesis equation by n over 2, half of the length of the signal. And for imaginary part, we divide the imaginary part by n over 2. Okay, but this is true for all the points other than the first and the last point. Okay, because it is starting from 0 to n over 2. So for first point it will be different. It is valid for, it means it is applicable for only the points between the first and the last one, between 0 and the n over 2. So what about 0 and the n over 2 point? We'll see in the next. Let us consider a point signal, 32 point signal. Okay, we know that if we have a 32 point signal, its DFT will be equal to n over 2 plus 1, 17. N over 2 means 32 divided by n over 2 is 32 divided by 2 is equal to 16. Then n plus 1, n over 2 plus 1 will be equal to 16 plus 1 equals to 17. So its DFT will consist of 17 sines and 17 cosine waves, right? And each of these will have 32 points. So the 32 point signal is decomposed into, can be decomposed into 17 sine and 17 cosine waves like this one. This is the first one, C0 cosine and CS0 sine. As we saw in the basis functions are represented with C and S. C means cos and S means sine. So C0 means that the one with zero frequency. Cos of 0 is 1 all the time. It is 32 samples, okay, equal to the length of the original spectrum or original signal. Sine also, sine of 0, zero frequency, it is equal to 0. Sine of 0 is, you can memorize it with sine 0 is 0, so the whole length of the signal will be 0, and the length of this will be equal to 32 samples as the original one. So the second component, this is the first one, then the second one will be cos of 1 and S of 1 means 1 frequency, and the third one will be C2 and S2 with 2 frequency and 2 frequency. So out of all those 17 components, we have chosen a few for demonstration. We have chosen actually 4 only, like this one, this is first one, and then C2 S2 having 2 cycles, okay, each. This is a cos starts with pi over 2 and sine starts with 0, okay. So this is cos 2 and this is sine 2, and the next one is 10. So it has 10, 1 2 3 4 5 6 7 8 9 and 10. So 10 cycles, and similarly sine 1 2 3 4 5 6 7 8 9 and 10 cycles, okay. And the last one will be 16th, okay, because first is 0th, so the last 17th one will be C16 and S16, like this. So it will have 16 cycles here. So these dots are actually the samples, okay. So just remember that the length of each component, each basis function will be equal to the length of the signal, okay. The original length of the signal, like here's 32 points, so each will be 32 points, and there will be 17 sine components and 17 cos, means 17 real and 17 imaginary. And you must be thinking that these are discrete forms, but how about these continuous lines here? So these continuous lines are just for the means for easy visual observation of the signal waveform. If I remove this from here, it will be difficult to imagine what is the shape or what is the form of this signal. So just this is just for uh, the demonstration purpose. Actual values are these black spots only, okay. So the line is not the part of discrete spectrum or discrete signal. Okay, the sum of all these points, like C0, then C2, C1, C2, C3 until C16, so each point will have a sum. So each of these components will give us one value, which will be the amplitude of that frequency component in the DFT, okay. So sum of all these points in each of these C and S components form amplitude of cosine and sine waves in REX and REX and IMX, means real part of X will compose of the amplitudes of cosines, and IMX, let me write it for you to remember that again. So REX and IMX. So this one will contain the amplitudes of these components S0, S1, S2, S3, S4 and so on, and this one will contain the sum or the amplitudes or sums of these components C0, C1, C2, C3, C4, C10 until C16, okay. Now if you notice here that the first component of sign here is 0, it is not making any difference. So this one is 0, and the last component is also 0. How? Because each sample here is at 0 line, right? So there are values existing up and down, but our sampling rate determines that the value at what the time at what we are sampling, it crosses the 0 line. So all the samples are at 0. So this one is 0 and this one is also 0, but the cos in the first one it is 1, and in the second one, I mean the last one, it is also at the top of the amplitudes. Okay, here, so it is at the maximum amplitudes, and this one is at minimum ones, the ones that is crossing at 0. This is 0 and this is 0 also. So the first and the last components of sine or the imaginary component do not contribute to the whole synthesis process. Okay, because they are 0. This is 0 and this is also 0. That is why the first and last components are different. So the first and last components are calculated like this. So the amplitude of the real part x is by Rex, first one, 0 means the first point, divided by n. So all other points are obtained, the amplitude of all the points is obtained by it dividing by n over 2, but the first point is by n and the last point also by dividing Rex n over 2 by this. N over 2 represents the last point by n. Okay, so the amplitude of first and last point is obtained by dividing Rex real part by n and the last point or also by n. Why is it so? We will see in next slide. This is the whole process of converting frequency domain signal into time domain. If you look at this here, so this one is a 16 point signal here. Okay, this is the frequency domain, and in frequency domain we know that it must be equal to n over 2 plus 1, means it is equal to 17, right? So if it is frequency domain, the time domain signal will be twice of it. Okay, minus a couple of points. So this one has 17 points, 0 until 16, means that the total number of points in the time domain will be equal to how many? 32, means that in time domain the total must be equal to 32. So here each point, like in the previous previous slide, you saw that, for example, here Rex of k, that was equal to Rex of k, or we leave it blank, divided by n over 2. Okay, so since n is 32, n over 2 must be equal to 16. So this value is actually 32. This is 32. Okay, so other than, we divide this other than first and last point. So first point will be divided by Rex, first will be divided by n. N is 32. Okay, so for the first and last will be different. We start with the second one. So actually this whole part is actually 32. Okay, so all the points are at 32 level. So starting from the point number 1, the sample number 1, until sample number 16, sorry, until sample number 15, we will divide by n over 2. N over 2 is 16, so 32 divided by 16 will be equal to 2. Okay, so all the points are 32 divided by 16 equals to 2 here. Okay, all the points other than first and last point. So first and last point will be divided by how much? 32. Okay, so 32 divided by 32, because this is the point here. So this point will be divided by 32 and rest of these points will be divided by 16, and this one will also divided by 32. So 32 divided by 32 and 32 divided by 32, this is 1. And after that we will use it and multiply it with our basis functions and we get time domain signal. This is an impulse function. So this is an impulse function. So this is a very famous function. We have seen it before. So impulse function in time domain, its frequency domain representation will be a constant value. Okay, like this. So this is very important. If you are asked a question like this, you must be able to answer that. What is the frequency domain representation of an impulse function? So if that impulse, for example, it is at 32 here, the impulse is at 32, then its frequency domain will be a constant value of 32. If it is at 1, its frequency domain will be a constant value at 1 here. Okay. Okay, now why we have to divide these first and last point by n and others by n over 2? Why is that? So we see in the next slide this thing, why we have to do this one. So rest all we divide by n over 2, but the first and the last part by 2 only. Why is that so? It comes here. So actually the frequency domain is defined as the spectral density, and spectral density is defined as the signal, how much of the signal amplitude is present per unit bandwidth. And how we found out bandwidth is by drawing these lines between these samples, okay, right in the middle of the difference between these two. So if the sample number 1 is here, we will, and the second sample is here, we will draw a line between sample number 1 and 2, means at 1.5. okay, the next line will be at 2.5, 3.5, 4.5 and so on, and the bandwidth for each sample will be the area between the two lines around it. Okay, and this one is described in as a fraction of the total bandwidth. The total bandwidth here is n over 2 in frequency domain, and n is actually the number of samples in time domain. Okay, so if this is 1, if it is from 4.5 to 5.5, for example, it is 1. Okay, we can do it like this, we can write it like this: 4.5 5.5 minus 4.5 is equal to 1. We divide it with the full bandwidth. Full bandwidth is n over 2. So we divide it 1 over n over 2. So it will become 2 over n, right? So this part is, this width is 2 over n. But for the last ones have half of it. These do not have any bandwidth on the other side. The last one does not have on the right side, and the first one does not have on the left side. So this one is half, means from 0, or we consider this one, the first one, 0 until 0.5. So 0.5 minus 0 is equal to 0.5. okay, so we represent it as a fraction of the full bandwidth. It will be, or we can write it like 1 over 2, right? So 1 over 2 divided by n over 2. So this 2 will be cancelled out with this one, and we will be left with 1 over n, okay, which is this one. And same goes for this. And that's all for now. And if you have any questions, we can discuss that on Kaizala or in the next live sessions. Thank you very much.